For the first time in recorded history, humanity's two most advanced space observatories, the Hubble Space Telescope and the James Webb Space Telescope, have been simultaneously focused on a single target, an interstellar visitor named 3I Atlas. This event is extraordinary on multiple levels. Hubble and Webb are rarely aligned on the same object. Each telescope was designed with distinct missions in mind. Hubble, launched in 1990, has spent more than 3 decades delivering sharp images in visible and ultraviolet light, providing detailed maps of galaxies, nebulae, and star-forming regions. Webb, launched in 2021, was designed to see the universe in infrared, to peer through dust, and to uncover the chemical fingerprints of distant worlds and the earliest galaxies. Coordinating these two instruments to observe the same moving target across multiple wavelengths is a logistical and scientific feat that required months of planning, negotiations across multiple space agencies, and real-time adjustments to account for orbital mechanics, telescope constraints, and the object's rapid trajectory. Yet 3I Atlas has forced this unprecedented collaboration. Its unusual combination of properties, brightness, chemical composition, and trajectory, has captured the attention of astronomers worldwide. Hubble, in low Earth orbit, is mapping the comet's expanding coma, the massive halo of dust and sublimated gas surrounding the nucleus. These observations reveal not only the scale of the object's activity but also its complex structure, hinting at jets, localized eruptions, and variations in brightness that suggest a dynamic, active nucleus. Webb, nearly a million miles away at the Sun-Earth L2 point, complements Hubble by probing the object in infrared. Its instruments break down the light into detailed spectra, revealing the molecular makeup of the ices, dust grains, and organic compounds. It detects chemical fingerprints invisible to Hubble, allowing scientists to examine the very building blocks of a planetary system far beyond our own. This combined observation is unprecedented. Never before has an object from another star system been simultaneously studied with such complementary perspectives. It is a rare alignment of technology, timing, and opportunity, a cosmic coincidence in which human ingenuity meets an interstellar messenger. As the telescopes point, engineers monitor sensors, scientists analyze preliminary images, and data streams begin to flow across the globe. Each observation is a potential discovery, a fragment of a story that has traveled across the galaxy for billions of years to reach our neighborhood. Hubble's latest images, captured in July 2025, are some of the most detailed ever taken of an interstellar body. They show a huge, ghostly halo surrounding a nucleus only a few kilometers wide, far smaller than the dramatic brightness of the coma would suggest. Estimates indicate that 3I Atlas ejects between 6 and 60 kilograms of gas and dusty material every second. To put this in perspective, imagine watching an automobile's entire mass disperse into space minute by minute. This level of activity is unusually high for such a small object, and while it could be the result of its first exposure to the sun after billions of years in darkness, the intensity still exceeds early predictions. Webb adds another layer of insight. Its infrared spectrometers have detected water ice, carbon-rich grains, silicate minerals, and a suite of complex organic compounds, some of which resemble the types found in the coldest, oldest regions of the Milky Way. What makes this remarkable is not merely the presence of these chemicals. They exist in many comets, but their pristine condition. Webb's data suggests that many of the molecules have undergone almost no thermal processing or radiation damage. This implies that 3I Atlas may have spent billions of years in an undisturbed region far from any star's influence, effectively becoming a sealed time capsule from a different planetary nursery. When scientists combine Hubble's structural imaging with Webb's chemical analysis, the object becomes a kind of natural spacecraft, carrying information about environments that formed long before the sun ignited. Never before has an interstellar object been examined with such depth, resolution, and precision. As the observations accumulate, astronomers are finding more questions than answers. One of the first anomalies involves the orientation of the dust plume. In most comets, solar radiation pushes dust away from the sun, shaping the tail in a predictable direction. But part of 3I Atlas's dust stream appears to bend toward the sun. The only known natural explanation is an unusually heavy population of dust grains or pebbles that are not easily repelled by solar photons. While not impossible, this configuration is rarely seen and requires highly specific conditions. Another puzzle involves the brightness of the coma. For a nucleus only a few kilometers across, the glow is significantly more intense than expected. It would require either a highly reflective composition or a mechanism releasing material at far higher rates than the models predict. Some researchers suggest that the nucleus might have an unusual shape, rotation pattern, or internal layering that causes volatile ices to erupt unpredictably. Others speculate that its outer layers might contain exotic compounds that vaporize in ways we haven't fully modeled. Then there is the matter of the orbit. 3I Atlas's path path is retrograde, meaning it travels opposite the direction of most planets, yet it lies only about 5 degrees off the ecliptic plane. Interstellar objects normally enter the solar system at random angles, as they are not gravitationally bound to our Sun. But this one's angle is peculiarly aligned, almost as if it had been gently guided by a chain of gravitational influences before arriving. Some astronomers note that its sequence of near encounters with Venus, Mars, and Jupiter has an estimated probability of around 1 in 20,000. This does not prove anything unnatural, but it raises the possibility that we are seeing a new category of object whose dynamics are still poorly understood. No single inconsistency is conclusive on its own. Yet the combination, the dust behavior, the unusual brightness, the pristine chemistry, the orbital alignment, forms a constellation of small mysteries that challenge our assumptions about what interstellar debris should look like. 3I Atlas is traveling at nearly 60 kilometers per second, and its window of visibility is shrinking. In just a short time, it will slip behind the Sun from Earth's perspective, creating a forced blackout period during which neither Hubble nor Webb can safely observe it. Unfortunately, this alignment occurs precisely during perihelion, the moment when the object should be most active, when its ices will sublimate most rapidly, revealing deeper layers never touched by light. For scientists studying interstellar chemistry, this is equivalent to losing access to a laboratory sample at the exact moment it becomes most valuable. The frustration is intensified by the presence of several spacecraft in different parts of the solar system. ESA's JUICE mission, NASA's Psyche probe, and Japan's Martian orbiter all lie within distances that could theoretically provide valuable data if redirected. The boldest proposal involves NASA's Juno spacecraft, currently orbiting Jupiter. In principle, Juno could perform a complex maneuver to slingshot into a trajectory that intersects with 3I Atlas in 2026. However, Juno's main engine is unreliable, and its fuel reserves are critically low. Redirecting it could cut the mission short or even leave the spacecraft stranded. Operations teams must weigh the potential scientific breakthroughs against the risks. A successful maneuver could provide humanity's first close-up view of an interstellar object, revealing surface structures, textures, jets, and mineralogy impossible to observe from Earth. But a failed maneuver could jeopardize years of planned science and billions of dollars in investment. This dilemma creates a rare moment where planetary science, engineering, and long-term strategy collide. 3I Atlas is not just an exotic curiosity, it is a messenger from a different part of the galaxy. Its frozen interior may contain material older than the Sun. Its dust may preserve the chemical fingerprints of worlds that formed in a star system entirely unlike our own. The decisions made in the coming weeks will determine how much of that knowledge we capture before the object fades into the outer darkness, never to return. Once it leaves, there is no technology on Earth capable of chasing it. This is a one-time encounter. If it is an ordinary comet with unusual quirks, it will help refine our understanding of interstellar chemistry. If it turns out to belong to an unfamiliar category, it will reshape how we model the formation of planets around other stars. And if its oddities point to something we do not yet have the vocabulary to explain, future generations will revisit these weeks in scientific archives, wondering why the clues were not recognized sooner. Whatever the truth may be, the opportunity is fleeting. Our instruments are pointed, the sensors are recording, and the object is bright for now. If you enjoyed this video, smash that like button, subscribe, and let us know what you think in the comments below. Thank you for watching.